for our analytical acceleration analysis. This is in section 7.3 on page 358. By example, let's do problem 7-4A on page 380. Someone have the book with them today? Thanks. So if I look at this problem right here, so you are to do, for your homework, you're to do row C. That's the problem that you've been doing that you did for position. That's the problem that you did for velocity. You'll need those values, the theta values from the position, the omega values from the velocity, in order to complete this problem, row C here. So you are to do this problem for the homework. What we've been doing in class for your notes, if you look back, the row A, we've done it for position, and we've done it for velocity. Now we're going to do it for acceleration. You have the position and the velocity derivation, if you will, in your notes, or solution in your notes, because we're always doing row A when we do the notes. So if you look at row A here, we have D is equal to 6, A is equal to 2, B is equal to 7, C is equal to 9, theta 2 equals 30, omega 2 equals 10. Unfortunately, alpha 2 is 0, so I probably should have picked another one at the beginning of the semester, but this still works. There's still an acceleration component because of your omega. And then RPA is 6 and delta 3 is 30.
Is alpha 2 going to be on the graph or just for the math part?
Say again?
Is alpha 2 going to be on the graph or just for the calculation when I use equations? Because it would matter if it's 0 or not.
Right. So we're going to derive it with alpha 2 in the equations, and when we plug the number in, it's just going to be 0 in that case.
So there is nothing on a drawing or anything?
No.
Okay.
No. So let me write this out here. So I got A is equal to 2, B is equal to 7, C is equal to 9, theta 2 equals 30 degrees, omega 2 equals 10, that's in radians per second, and alpha 2 equals 0 radians per second squared. All right, so the units are radians per second squared, and on your alpha component, and we have radians per second on omega, and we have degrees on degrees. And these will be in centimeters. All right. Let me draw you what this thing looks like, what this configuration looks like. So this is O2, and at 30 degrees from there, and 6 units out, so this is O4, and D equals 6 here, and 30 degrees from here, I'm I'm looking at something that's out here somewhere. And that's 2 units out. And then I have this angle right here up to here is my theta 3 that I found earlier, which turns out to be 88.837 from my position analysis. So you have to do the position analysis first. Done earlier.
Is this open or closed?
This is going to be, I'm going to just do the open configuration here. So that's a good point. So let's just do the open configuration. All right, but the same principle applies for the cross configuration. Okay, same equations. So this right here is 88 degrees. So that's something that's about right there. And that is 7 units long. So this is A is equal to 2, B is equal to 7. And then I have from here, this is C equals 9, and this one here, I know from earlier that theta 4, and let me put open here, and let me put theta 3 open here just to be clear. Theta 4 open equals 117.286 degrees from position analysis done earlier. All right. And this right here, I've got this in. So I'm going to go ahead and do that now, which is my theta 2 equals 30 degrees. All right. So I'm not going to derive the equations for this. It's going to be an end user of the equations. Let me show you how you apply those. This is on page 360, so we use 7.12c on page 360. And that says that A equals C times sine theta 4. Plug 9 in, sine, and this is from the open configuration, so it's 117.286 degrees. And that equals, when I do the math, 7.99. So I would suggest that you carry these things out to 3, sometimes 4 decimal places, but at least 3. B equals B times sine theta 4, which equals 7 times sine of 88.837 degrees. And this is from the open configuration. When I do the math on this, I get 6.999. C is a rather long equation, so I'm not going to write that out, but you can look at that page in the book and look at equation 7.2 12C. And that, when you do the math on that, should be 244.05. D equals C times cosine theta 4. When I plug those values in, I get minus 4.126. E is equal to B cosine theta 3. When I plug those values in, I get 0.142. And then F is another one of those long equations like C. So I'm not going to write it out, but if you plug the numbers in and verify that you're using the equation correctly, you should get minus 223.727. Those are the constants involved in this. We go ahead and use those in 712A, which says that alpha 3 equals, and since we're doing an open configuration here, we have to use these values from above, equals C times D minus A times F over A times E minus B times D. When I plug those values in from here into this equation, I get 26.075 radians per second squared. And that is your alpha 3 open value. I'd ask for you to box your answers. It makes it a lot easier to grade it when you box your answers. And we use 712B to find alpha 4 open. And the colors of this don't mean anything. I'm just trying to highlight it. CE minus BF over AE minus BD. And that equals 53.327 radians per second squared. And that is your alpha 4 open. Box that in. All right. Next, do cross configuration. Where I know that yeah, the thing that I did not put down. Let me go back to this one here. This is kind of important. I should have put this down. So go back to the previous page, and I have my omega 3 equals minus 5.991 radians per second squared, or second. Right? This is from velocity analysis performed earlier. Okay. And my omega 4 equals minus 3.992. And the signs are important to carry this along. Radians per second from velocity analysis performed early. So for you, earlier means that you look back at the old homework. If you didn't keep the old homework, remember the answers to these things are in the back of the book. So you can look at that. So that is, again, for the open configuration here. And for the cross, next to cross configuration, and for these, you're using all the values that you found earlier in position, found earlier in position, and I get theta 3 cross equals minus 115.2 degrees. Theta 4 cross is equal to minus 143.6 degrees. And again, if you don't have that old homework, you can look back in the book, back of the book, to find what those values were. And then found earlier velocity, I have omega 3 cross equals minus 0.66 radians per second, and omega 4 cross, if I look back at that, was minus 2.66 radians per second. And that would be on page 829 in the back of the book if you don't have that old homework. Use those values, so these yield your alpha 3 cross as equal to 77.9 radians per second squared, and your alpha 4 cross equal to 50.7 radians per second squared. And you can verify those by looking at page 828. I said earlier that in this problem, unfortunately, but actually it may be fortunate because now I'm able to illustrate a point. Remember that alpha 2 in the problem statement was 0. But yet, we're getting acceleration components, angular acceleration components for alpha 3 and alpha 4. And the reason why that is because of my omega 2 value as it's spinning going towards the center, so there's an acceleration component there, which is transferred to link 3 and link 4. So just because your alpha 2 value is 0 does not necessarily mean that your alpha 3 and alpha 4 is 0. Okay? Because of the centripetal acceleration. All right, so that is the 4-bar, and what I did was, on this, I went ahead